Welcome to our representation. Our research paper is 79607, the response mitigation of floating platform by Porous-Media tuned liquid dampers. My name is Wenhuai Cao. This work involves the Keys group at LSU and the Manuels group at UT Austin. You're welcome to check out our group website. The target of this research is to provide a high-fidelity numerical tool for fluid structural interaction problem. We especially aim at the structural vibration control for offshore structure and all kinds of vessel on the ocean. We further validate a new type of vibration absorber for the floating platform. This damper is a water tank filled with porous media. We call it a Porous-Media tuned liquid damper in our paper. And besides, we have developed several numerical methods based on the potential flow model and the Navier-Stokes flow model. The major challenge comes from the numerical algorithm that need to couple the CFD and rigid body dynamics, because this is the key point for an accurate and efficient numerical simulation. In this paper, we consider a two-dimensional problem that involves the surge, heave, and pitch motions of the floating body. The interaction between the PMTLD and the floating body undergoing wave excitations will be characterized. And this research can be extended to some three-dimensional problems in the future. There are three numerical configurations. Two of them are based on the potential flow theory, and the other one is based on the Navier-Stokes flow model. The first configuration solves the flow field by an Eulerian-Lagrange method via boundary element method. So this method is fully nonlinear. In general, it assumes the ambient wave is inviscid. But for the slushing problem, the linear and nonlinear damping effect due to Porous-Media have been included. And the second one solved the sloshing problem in the TLD by a mechanical model. This model transfers the sloshing fluid into several sets of mass brain dashpot systems. It can reduce the degree of freedom, therefore it not only accelerates the numerical simulation, but also make it easier to design. The third one solved the two-phase Navier-Stokes flow. The flow computation involved finite element method and level set method. The computational cost is higher, but it includes the most complete physical information. And we have different fluid structure interaction algorithm for these two models. For the potential flow model, the fluid force is not a prior known variable. It is solved by the Eulerian-Lagrange method, which needs the body kinematics as a boundary condition. And therefore, we need an iterative algorithm to ensure the dynamic equilibrium between fluid and solid phases. And if these two solvers converged, then the Newton's second law is ensured within one time step. Then we go for the next time step. And for the Navier-Stokes flow model, we take advantage of the open source CFD tools. It's called the Proteus and the multi-bottle simulator Chrono. And you are very welcome to check our website for more information. And in this case, we solve the fluid flow to get the total force on the solids from the integral of a stress, which include viscous shear forces and the normal forces. Then we solve the solid dynamics to get the new configuration at the next time step, then repeat. And to design a TLD, we can correlate the mechanical model of the PMTLD with two mass damper. Therefore, the following design equation can be useful for a given mass ratio. The tuning frequency ratio and the optimal damping ratio will be obtained accordingly. But here you see the frequency of the main structure appears right here in this section. So we have to identify the dynamic characteristic of the floating body first. So according to the free vibration test, the natural frequency of the pitch motion of the floating body is 0.61 Hertz. Therefore, we can calculate the tuning frequency and design the tank dimension since they are correlated. Since they are for an optimal damping ratio, we have to adjust the permeability of the porous media. I would like to also clarify that because of the nonlinearity of the sloshing phenomena and the changing damping effect of the ambient wave, the real optimal parameters may not be exactly the same as shown here. However, they are very close. So this is a video of a controlled and uncontrolled floating bodies undergoing resonant wave excitation. So first of all, we found the reduction in surge motion is not obvious, and the PMTLD seems ineffective for heave control. However, it is very effective for reducing pitch motion. The reduction ratio is nearly 70%. From the observation, we can categorize the control mechanism of the PMTLD as three phases. There are force cancellation, energy transfer, and energy dissipation. As the wave hits the floating body, the sloshing force cancels out the wave loading, so the energy is transferred to the PMTLD and then dissipated. Therefore, two key points for a good PMTLD are phase cancellation and high damping capacity, which are validated in our resonant test. And finally, we're going to validate the overall performance by frequency response curves at near resonant conditions. When the PMTLD is applied, the frequency shift because of the additional degree of freedom of the TLD system. The PMTLD can reduce the pitch motion responses by up to 80%. So both the potential and the Navier-Stokes flow model give similar results. So this implies the damping from PMTLD is more important than the wave-induced damping. And besides, the single degree of freedom mechanical model shows similar results. It means the first modal response of PMTLD dominates. From the study of this paper, some conclusions can be drawn. Number one, since the eddy making damping of the ambient wave is minor compared to the energy dissipated by porous media, the potential flow model for PMTLD analysis can be useful, although the Navier-Stokes flow model includes all kinds of viscous effect. And number two, the mechanical model also gives same result because most of the time the first modal response and the linear damping term of the PMTLD dominate. The mechanical model is good for design. And last but not least, PMTLD is very effective for pitch motion mitigation. The overall response reduction can be up to 80%. It can enhance the workability and comfort of the floating workstation. However, heaving control is not validated, and the effectiveness of surge control is uncertain in this paper. Now, in the future, we will focus on the parametric study of PMTLD and its application to more complex three-dimensional dynamic analysis, such as wind turbine design. Thank you very much for your attendance. If you have any comments, please feel free to send an email to me.